I very much enjoy building microelectronics, and this is my latest creation. It's an earring with LEDs in it. Now inside here we've got 6 LEDs, a programmable microcontroller, and a power source. That's the biggest part. I'm using a CR927 battery, which is the smallest commonly available lithium coin cell. Just for a comparison, here's an ordinary CR2032, and here's a 927. Now you can get smaller coin cells. The zinc air ones that you get in hearing aids come a lot smaller, but they only produce about 1.5 volts, so in order to light an LED we would have to stack them. Or fit a boost converter, I suppose. I think lithium's the only practical option, so our size was basically dictated by this battery. The microcontroller is an Atmel AT-Tiny 9, and if you've not seen these before, then you're in for a treat, because these things are minuscule. In fact, the entire point of this project was just to find some situation where you'd actually need a chip that small. It's got 32 bytes of RAM, 1 kilobyte of program space, and 3 usable I/O pins. The 6 LEDs are Charlie-plexed, and done so in a way that they have individually addressable PWM brightnesses. Also, here's an AT-Tiny 85. Just looks enormous in comparison. To turn this on, we have to press the switch, which is hidden on the stem that connects to the hook. This was a very difficult part to manufacture. This first mode is just showing off the ability to light any of the LEDs at any brightness, just a swirling pattern. We press the switch again and it goes to the next mode. This one is flashing a message in Morse code, and at the moment it's just a test message to ensure it's working. I had to slow the Morse speed right down because I found that visual Morse code is a lot harder to understand. You have to kind of hear it in your head. The way I've written this, the message could be up to 128 characters, but the only way to change it at the moment is by reprogramming the chip, which means completely disassembling everything. So I was thinking, maybe for the next version, if we used an AT-Tiny 10, which has an analog to digital converter, you can use the ADC to read the LEDs as a light sensor. Then get it, if we put it into learning mode by double tapping the switch, say, then you could flash a new message with a torch. The problem is, where do we store that message? The chip can't write to its own program memory, so it would have to go into the RAM, which means it would be limited to about 20 characters. But if all you wanted was to say a person's name, maybe that would be enough. Anyway, the last mode is using a linear feedback shift register to get a pseudo-random number generator to flash the LEDs in a reasonably random way. It doesn't look quite like I was expecting, but it's pretty interesting. And the final mode switches it off again. The chip goes to sleep, and the power draw on the battery is small enough that it should have a shelf life of several decades. And while the LEDs are on, the battery should last for about 10 hours. So, we have one earring, but to be earrings, we need to build another. And this time I will attempt to film the process, which does make it harder, but I'm feeling confident. So this is what you'd use to make an ordinary circuit board. It's copper-clad FR4, which is a fiberglass epoxy composite. But you can also get copper-clad polyimide, also known as Kapton, and this is sold under the trade name Pyrolux. So if we etch our circuit onto this, we'll end up with a flexible PCB. And my method of etching involves ferric chloride, spray paint, and a laser cutter. So I've got my ferric chloride, I've got my rubber gloves on, and the way I like to do this is I just dab the smallest possible amount onto it with a sponge, and this means that everything that's left in the bottle is at full strength. It takes about 20 minutes to etch. So what I do is just every few minutes give it a bit of an agitation, because you have to be careful not to scrub too vigorously, because that would take the paint off. And I'm only concentrating on the middle section because we're going to be cutting these tabs out with a pair of scissors anyway later. Now, since the Kapton is transparent, it's very easy to see where the copper has etched away and where some bits still need a little more acid. Now at the point of dabbing it dry with a piece of kitchen towel, a couple more places it could do with a bit more acid, but I don't want to risk over etching it. It's such a small circuit, we can touch it up with a Stanley knife afterwards. There is probably a better solvent for this, but this is all I have to hand. For surface mount chips, I'm a big fan of these IC test clips that let you reprogram a chip even after it's been soldered down. Like that. So these are great, but I couldn't find one for SOC23, which is what the AT-Tiny9 uses, so I had to make up this kind of dodgy adapter. Ignore this part, that was an idea that didn't work, but just here we've got a bit of copper-clad FR4 with some lines scraped into it, and the ISP cable connects here. Of course it doesn't speak ISP. The Tiny9 chip uses the Tiny Programming Interface, it's called, But luckily for us, the USB ASP and the people who make AVR Dude have already added support for that, so that's great. It's not exactly convenient, but with just the right amount of finger pressure, it is usable. Okay, that did take a couple of attempts, but it has successfully programmed the chip, and now we're ready to solder. I don't have a reflow oven, but even if I did, I would not feel confident reflowing this. Now, it's absolutely essential we get these LEDs the right way round, otherwise they will flash in the wrong order, and that would be dreadful. Well, the soldering's not particularly beautiful, but it will have to do. Of course, we can't actually test this until we've completed the whole ring, because that lead is a jump to this side. And before we can do that, we have to build the switch. So this tab is the positive terminal to the battery. Which is on the rim. And this big tab will be the negative terminal, and this L shape will be the switch that will contact this plane here. But first we have to join this pin to that pin. So the switch operates like this, and hopefully the springiness of the Capton will give it an acceptable number of actuations. Well, fuck. I'm going to blame this on having this enormous camera in the way, but it seems that a couple of my solder joints have failed and we've got two LEDs not working. I swear the first one worked first time, so let's take this apart and see if we can fix it. So this LED had failed, and its anode is connected to that wire, and this LED wasn't lighting up either, so its anode is also on that line, so it must be that that line is not going high, and that would be the problem. So this would be the ground plane, and there's a little bit of copper left, and it's bridged. I don't know why I didn't cut that closer, really. Still, it should be an easy fix. There we go. Good. So the circuit is now finished, and we can start work on the case. I spent a long time trying out different materials for the clear part of the case, and I assumed it would be possible to just laser cut a ring of acrylic like this. But I had great problems with this. When you cut it too thin, the edges become melted, and even if that doesn't happen, my laser cutter is so low resolution that the steps become evident when you try and do a circle. Also, acrylic is surprisingly brittle. This one's broken with very little force. I have some glass test tubes, and I've used them before when I tried to make this tiny Stirling engine, but the diameter here is just a little bit bigger than what I wanted for this circuit. You can of course reduce the diameter, it's very simple glass blowing, but the problem is it becomes unbelievably brittle. Like you just touch it and it shatters, unless you anneal it. But in order to anneal it, you have to cool it down over the course of an entire day in a kiln. So glass is just impractical for me. I was going through various bits of tubing I had, and I eventually found these syringes. They come in all different sizes, and this particular one was just, I think, 1 millimeter bigger than what I was originally planning. So that's almost perfect, really. It's a little annoying that it's not crystal clear. It's kind of translucent, really. But the benefit of this is that it's elastic. So we can do a press fit on the end caps without worrying about it breaking. in a moment, we're going to have to drill a very small hole. Tiny drill bits are actually very cheap. They're basically disposable. They come in a thing like this. But to use them, they absolutely have to be centered. An ordinary Jacob's chuck like this doesn't actually close to zero, so you can't hold them at all. This really nice ROM chuck does close to zero. But as a result, it doesn't have the detents, which are used to keep it centered as you tighten an ordinary chuck. So as you're closing it, it's very easy for the drill bit to get caught between just two of the jaws rather than three. So it's the same deal on the chuck on this mini drill. Maybe because the bearings are quite old, you can actually hear when the drill bit is not centered. The vibration is completely different. So the only solution I've got for this is to repeatedly loosen it, rotate the drill bit a bit, and then tighten it again. And by chance, eventually it'll hold it on center. And it is absolutely essential to get this right if you want your tiny holes to be successful. Especially so here, since for what I'm about to do, I don't have a cross-drilling jig, so it's going to be a handheld 0.5mm hole in a 1.5mm part. Pretty cool, huh? The Morse code message in this one is different and a little more appropriate. The source code for this I'll stick up on GitHub, and one of the things I didn't do is seed the pseudo-random number generator. I was going to. You could have it save its state as it leaves the mode, and then next time start up where it left off, so the pattern never repeats. But there's no point, because visually you're not going to recognize anything beyond the first few seconds. And by having it start at a fixed position, it opens up the possibility of synchronizing them. Okay, it's been about 10 minutes now and they're pretty far out of sync, so perhaps I should have calibrated their internal oscillators beforehand. I will probably make a laser cut case for these or something, but this video has already gone on way too long, so I think I'll leave it there for now. There's a load more information on mitzella.com, where this project started out as an investigation into the different ways of charlieplexing. Have a look at that if you're interested. See ya.